Today we are going to be learning about
Titrations! What's up, guys? It's Fiona back here again. Today I'm going to be teaching everyone how to interpret titration curves. First up, what is a titration curve? You're probably wondering. Well, a titration curve is simply a recording of the pH of a solution as it is reacted with another solution. So, for example, reacting an acid with a base or a base with an acid. Now, titration curves can tell us a lot. It can tell us a lot about the strength of the acid or the base that are being reacted, and it can also tell us about the equivalence point and the point of equilibrium in this reaction. So, for starters, when you get a titration graph or a curve, it's going to look something like this. So, just simply looking at titration curves, we can tell a lot based on just the shape of the curve and pH. So, if we look at this graph right here, for starters, we can determine what is being reacted with what, just by looking at the starting and ending pH. So looking at this graph here, we have a starting pH of approximately 13, settled between 12 and 14 on this graph here, which is very basic. This is a strong base because its pH is so much greater than 7, which is neutral right here. Now, we can see that the ending pH is about approximately 2. So this is a strong acid because it has a very low pH. Now, looking here, we notice that there's a vertical line right here. This right here is known as the equivalence point, halfway between this vertical line. Now, the equivalence point in a titration curve, we can mark the equivalence point here as halfway between this most vertical section on this graph here. Now, the equivalence point is where the number of moles of the titrant is enough to completely react with the number of moles in the sample being titrated. And so it is usually marked right here in the most vertical section, and this is where equilibrium occurs. Similar to this, you can tell when it's an acid being reacted with a base. So you can see here that the starting pH is again below 7. You can't read it very well here, but you can see that it's below this middle point here. So we can see that this is probably going to be a strong acid, or at least an acid. Now, again, we can see that the ending pH is above 7, so you know that it was reacted with a base. Now, again, we can identify the equivalence point as being in this vertical section right here. You can see it right here. But what's unique about this graph that we weren't able to see, or you were able to see, but it's more clear on this graph in my opinion, is this right here, this area is known as the buffering region. Now, about halfway to the equivalence point is this buffer zone. This is where we use a buffer solution, which we will talk about later. We won't talk about later.
No, that's a strong base.
Okay, so now that we have our weak acid and our strong base, you can see here, this is the equivalence point here. Now, about roughly halfway to the equivalence point is the buffer. Put that point at say right here, roughly. Looking at these MCQs here, we're just gonna do number 2 and 3 corresponding to this graph here. So, which one of the following combinations does the titration curve represent? So looking here, we see, again, the pH is above 10, between 10 and 12, so it's again going to be probably a pretty strong base. And then again here, it's below 2, so again, it's probably going to be a very strong acid. So you can see that the starting pH is a base, so we're going to say that we're going to add a strong acid to a strong base because the pH decreases over time and becomes the pH of a strong acid. So that's going to be E right there. And now the pH of the solution at the equivalence point, again, the equivalence point is simply the most vertical section here, and then we're going to find about halfway between here, so we're going to go approximately there. Corresponding to this pH over here, that's about 5, and looking at these answers here, we're going to say 5.3 is the most accurate. Okay, now looking at this FRQ here, we're going to read real quick.
A solution of 0.1 molar HCl and a solution of 0.1 molar NaOH are paired. A 40 milliliter sample of one of the solutions is added to a beaker and then titrated with the other. A pH electrode is used to obtain the data that's plotted in the titration curve shown above.
We're just going to do these two right here. Identify the solution that was initially added to the beaker and explain your reasoning. Again, looking at this graph here, we can see that there's a low pH and high pH at the end. So we're probably going to assume that it's going to be a strong acid to start with. Looking at Identify the solution that was initially added to the beaker. Looking at HCl and NaOH, we can identify that this is a strong acid and this is a strong base. We know that because it's such a strong pH right here, and because HCl is one of our strong acids, we're going to say that HCl. Now, on the titration curve above, circle the point that corresponds to the equivalence point. Again, looking at this most vertical area, we can see that the point in the middle is approximately right here. So we're going to circle this point, and the coordinates are going to be 40 milliliters and a pH of 7. So 47. And that's that, folks.
So today, I'm going to be identifying different species on a titration curve.
In this example, we are titrating a weak acid, HNO2, with a strong base, NaOH. At the initial point of the titration, the only species present will be the weak acid, HNO2s. However, as we continue with the titration, we are going to be adding NaOH. Here, the base will fully dissociate due to the Arrhenius theory, creating Na plus and OH minus. The weak acid, however, will partially dissociate into H plus and the conjugate base, NO2 minus. The OH minus will neutralize with the H plus, creating water, as well as the conjugate base, NO2 minus, and as well as Na plus. This is what is present at point B of the titration curve. As we move on to point C, which is halfway to the equivalence point, we see that another NaOH is added. Here, there are two NO2 minuses as well as two HNO2s. The concentration of these two are equal to each other, and because the conjugate base is equal to the weak acid, in the equilibrium expression, they will cancel out with each other, leaving with Ka equals to the concentration of the hydrogen ion. Then as we reach the equivalence point, we see that there are two more NaOHs added. Here, the OH minuses will neutralize with the final H pluses, leaving there to be no more reactants to be reacted with. The solution has reached equilibrium. The pH at the equivalence point, however, will be greater than 7 due to the high presence of the conjugate bases. Then, as we move to the final point, point E, we see that two more NaOHs are added. Here, they fully dissociate, however, the OH minuses will not have any more hydrogen ions to neutralize with, leaving them to be present in the solution. Here, the pH of this will be greater due to the fact that there is a strong base, OH minus, as well as the conjugate base of the acid, NO2 minuses. Those are the species on the titration curve. Next, moving on with some practice. The first MCQ states, if we reacted a weak acid, HF, with strong base, NaOH, at the equivalence point, what would the pH of the solution be? Because it's a weak acid, we know that it will dissociate partially with creating a conjugate base of F minus. Here we know that it will fully dissociate into NaOH minus. This will be plus. Because of this, at the equivalence point, as seen in our example prior, we see that at the equivalence point there's going to be high concentration of the conjugate base. Because of this, it indicates that the pH will be greater because the solution will be more basic. With this, we can cross out C, D, as well as A, leaving to B being our correct answer. In this FRQ, we see that there is a weak acid, HNO2, titrated with KaOH, a strong base. Because of this, the KOH will split into K plus and OH minus. And because the weak acid will partially dissociate, we know that some of the molecules will split into H plus as well as NO2 minus. And the question here asks, explain why there's water present in the titration. When these split, the OH will neutralize with the H plus. Because of this, we have H plus and OH minus. And these two want to bond due to this having one electron to donate and this one electron wanting to be gained to be neutralized. This will turn into H2O. In this last part of the FRQ, we see that if we titrated NH3 with HCl, what would the pH of the solution be at the equivalence point? We know that the HCl will fully dissociate into H plus and Cl minus. However, because there's no OH to neutralize this H plus, there's going to be a lot more acid that is continuing to be present as we continue to add it to the solution. With this at the equivalence point around here, we see that there's going to be a lot more H pluses. This will indicate a more acidic solution, lowering the pH to be lower than the neutral of 7. So the pH will be less than 7.
Hey, Mr. Ritchie, we're gonna do a quick joke break real quick. Shayna, Do you know why I have so many bad jokes about chemistry?
Why?
Because all the good ones are gone.
How to find the Ka of a weak acid. For this problem, we need to calculate the Ka of a 0.5 molar aqueous solution of HCN plus H2O in equilibrium with H3O plus Cn negative with a pH of 4.88. The first step in this problem is to find the equilibrium expression, which is the products over the reactants. And we wouldn't include H2O because it is a liquid and only aqueous is included in the equilibrium expression. Step 2 is our ice table. We have our starting concentration at 0.5 and we need to subtract X from it to get to 0. So we also will start with a concentration of 0 for H3O and Cn, and we need to add X to find how much the concentration changes by. Step 3, we need to find the pH of H3O plus, and for that we would take the negative pH of the solution and then set that to 10 to the power of the negative pH to find the concentration of H3O, and for that we get 1.32 10 to the negative 5. Next, we would put our X into the equilibrium expression, and because we have two values, concentrations on the top of the problem, we would do X2 and 0.5 minus X, which would eventually turn into 1.32 e negative 5 squared, and 0.5 minus 1.32 e negative 5 after we plug our numbers in. And solving this gives us a Ka of 8.69 e negative 10. Next, for the MCQ, we have HCOOH plus H2O in equilibrium with HCOO negative plus H3O plus. And for this problem, we need to determine the acid dissociation constant, or the Ka, of a 0.2 molar solution with a 3% ionization. The first step for this problem would be to figure out which equation we're going to use, which is percent ionization is equal to the concentration of H3O plus over HCOOH times 100. And once we plug all of our numbers in, we get a concentration of HCO plus is equal to 6e negative 3 molar. And we would plug that number into the equilibrium expression to give us an expression of Ka is equal to 6e negative 3 squared over 0.2. And once we solve this, we get a Ka of 1.8 e negative 4, and by rounding our answer, we can figure out that the answer to this problem is B, or 2e negative 4.
Hey guys, so today we're going to be learning about polyprotic acids. So a polyprotic acid is a type of acid that is capable of donating more than one proton. So in the past few videos, we've been just looking at monoprotic acids, which are acids that Fiona was talking about that just have one proton being donated. Whereas polyprotic acids can have more than one, which creates a graph that looks like a step formation. And so the number of inflection points on the graph is the number of protons it can donate. So a step like this would be able to donate 2. So our MCQ is the Ka for the first dissociation of a polyprotic acid is always blank compared to the Ka for the second dissociation. So for this question, the Ka for the first dissociation is always going to be greater in value compared to the Ka for the second association. And this is because polyprotic acids are starting lower, like we learned with the pH. When the pH is lower, it's more acidic. So the pKa, which is the negative log of the Ka, is going to be lower on the graph, which means a higher Ka than any of these. So our answer is going to be greater than that. So now we are going to be doing the FRQ. So our first thing we're going to look at is the graph. So this polyproduct graph is a little harder to see than the other one, but what we can see is that there is a slight curve here, which is where the first one was being donated, and then we have our second one here, which is where our second hydrogen is being donated. So again, from the first video, we can find the halfway to equivalence point, which is going to be the in-between of these two most horizontal lines, or you can try to, I would normally say in the half of the vertical line, but this isn't very vertical. So you can see in between these two, which is going to be around here, I'd say around 15. And then to find our buffer, which we also learned about, you're going to take halfway from this point to the beginning. So that would be around, I'd say half of 15, 7.5, and this is going to correlate to around 1.5. So that's our first, and this is our pKa of the first hydrogen. For a second one, we're going to do the same thing, but instead of starting here, we're going to start at this equivalence point. So again, we're taking these 2 points, we're doing halfway to equivalence, which is going to be around a pH level of 8. And that's going to be like around 30. So we're going to take the halfway, which is going to be halfway of these 2 points, which is going to be around here, and that will leave a pKa, which a pH in pKa will be the same for this graph, pKa2 of 4. So now we're going to be finding Ka1 and Ka2. We have pKa of 1 and 2, so we're going to be using some of our equations to find the Ka. So because we know our pH and pKa is the same, like we can use the equations of the negative log, which the inverse of that would be 10 to the negative pH, or 10 to the negative pKa. And our first pKa, as we know, is 1.5, so our first Ka value, which gives you a value of 0.0316. And after that, we have our second pKa, which we're going to do 10 to the negative 4, which gives us a value of 0.0001. So these are going to be the answers of your Ka1 value and your Ka2 value. Find the Kb for the conjugate base of the Ka2. So our conjugate base is after one of the hydrogen atoms has been donated. So to solve that, we know that Ka plus Kb equals Kw, which is equal to 14. So we have 14 minus 4, which is our pH from the second Ka, and that's going to be equal to 10. So our pH of the conjugate base is 10. So we can use this 10 with the same equation and do 10 to the negative 10, which equals to 1 times 10 to the negative 10.